Hey there, cosmic explorers! Have you ever felt that thrill of standing on the edge of a great mystery, one that changes everything you thought you knew about the universe? Well, get ready, because today we are diving into one of the biggest and most fascinating secrets of the cosmos. We are talking about something omnipresent, yet totally invisible, that holds entire galaxies together. To really understand the scale of this mystery, I want you to imagine a merry-go-round, like one of those carousels you see at a fair that spins faster and faster. If the horses and the carriages on that carousel were not securely bolted to the ground, what do you think would happen? They would fly off into the distance due to centrifugal force. It is simple common sense, something we can all visualize. Now, let's take that exact same logic and scale it up to a cosmic dimension. Our galaxies, with their billions of shining stars, planets, swirling gas, and ancient dust, are essentially like gigantic cosmic merry-go-rounds. They spin, and they do so at a truly dizzying speed. Think of our own home, the Milky Way. It is a majestic spiral that completes one full rotation every 250 million years. That might sound slow, but its outer arms are actually moving at incredible velocities. Here is where we run into a giant problem. If we calculate the total mass of all the visible matter in a galaxy, meaning all those bright stars and all that detectable gas, and then compare it to the speed at which they rotate, the numbers just do not add up. According to the laws of gravity we know and love, these galaxies should be completely unstable. The stars and gas at the very edges, spinning so incredibly fast, should have long ago flown off into the void, just like those merry-go-round horses getting flung into space. By all accounts, galaxies as we see them simply should not exist. But here is the most astonishing part of the whole story. Not only do these galaxies exist, but they are incredibly stable and beautiful structures. The spiral arms hold together perfectly, stars follow their predictable paths, and galaxies do not disintegrate into scattered bits across the emptiness of space. It is as if there is an invisible glue, a kind of cosmic superglue holding them together against all the odds. This mysterious glue, which we cannot see, cannot touch, and cannot directly detect with even our most powerful telescopes, is what scientists have dubbed dark matter. It is the missing piece of the puzzle that finally makes the equations of the universe work. It is what balances the scales of the cosmos. Dark matter does not emit, reflect, or absorb light, which is why we call it dark in the most literal sense possible. However, it does have mass, and because it has mass, it has gravity. It is as if the vast majority of our universe is an invisible ghost that we can only feel through the strength of its pull. What exactly is this dark matter, and how can we be so sure it exists if we cannot see it? The story is about to get even stranger and more exciting as we unravel the secrets of this elusive substance. If the calculations of visible mass do not match the rotation speed of galaxies, and yet those galaxies persist, the only logical conclusion is that there is something else there. Something we cannot see is exerting a significant gravitational force. This idea is not as new as you might think. The first time anyone stumbled upon this strange anomaly was all the way back in the 1930s. An astronomer named Fritz Zwicky was observing the Coma Cluster, which is a gigantic grouping of thousands of galaxies. As he measured the speeds at which these galaxies were moving within the cluster, Zwicky noticed something incredibly odd. The galaxies were moving so fast that the entire cluster should have disintegrated. For the cluster to remain bound together, there needed to be much more mass than what could be seen with the eye. He called this missing stuff dunkle materie, or dark matter. At the time, his idea was met with a lot of skepticism, but Zwicky had planted the first seed of a revolutionary idea. Decades later, in the 1970s, a brilliant astronomer named Vera Rubin, along with her colleague Ken Ford, provided the most compelling evidence yet. Rubin was specifically studying the rotation curves of spiral galaxies. To understand what she was looking for, think of our own solar system. The planets that are closer to the Sun, like Mercury and Venus, orbit much faster than the distant planets like Neptune. This makes perfect sense because most of the mass in our solar system is at the center, inside the Sun, and gravitational pull naturally decreases with distance. Rubin expected to see something very similar in galaxies. She thought that stars further from the galactic center would orbit much more slowly than those near the middle. But what she found absolutely puzzled her. Stars at the very edges of galaxies were orbiting at the same speed as stars closer to the center. It was as if there was a gigantic, invisible halo of mass extending far beyond what we could see. This halo was providing the extra gravity needed to keep those distant stars from flying off. Vera Rubin's work was a massive watershed moment that turned dark matter from a scientific curiosity into an absolute cosmic necessity. Before we dive into what we think this matter might be, it is crucial to understand what dark matter is not. It is not simply normal matter that is just hard for us to see. Scientists call normal matter baryonic matter, and dark matter is definitely not that. For instance, it is not made of normal black holes. While there are black holes throughout the universe, and some are supermassive, there simply are not enough of them to explain the massive amount of dark matter we need to balance the books. Moreover, many of them would be detectable by how they interact with their surroundings. It also is not made of brown dwarf stars or rogue planets. These objects, which are sometimes called machos, or massive astrophysical compact halo objects, are made of ordinary matter that just does not emit much light. But extensive searches using an effect called gravitational microlensing have shown that there are not enough machos to account for the phenomenon. Gravitational microlensing is when the gravity of an object passing in front of a distant star briefly magnifies its light, but those signals are just too rare. Finally, it is not invisible gas or dust clouds. These clouds, even if they are dark, would still absorb or emit some radiation at other wavelengths, like infrared or radio, that our instruments could detect. No, dark matter must be something fundamentally different from everything we know. It is something that barely interacts with normal matter and, most importantly, it does not interact with light at all. If dark matter is so elusive, you might wonder how we are so sure it is there. We mainly detect it by its gravitational effect. Think of a gust of wind blowing through a field of wheat. You cannot see the wind itself, but you can see the stalks move and sway. Dark matter is that invisible cosmic wind that moves galaxies and groups them in ways that would not make sense without it. One of the most direct and visual pieces of evidence is something called gravitational lensing. As Einstein taught us, gravity does not just attract objects, it actually curves the very fabric of spacetime. A massive object can act just like a lens, bending the light from more distant objects sitting behind it. It is very much like looking through a wine glass, where the image of whatever is behind it gets distorted and stretched. When astronomers observe galaxy clusters, they see distortions of background galaxies that are far greater than the visible mass of the cluster could ever cause. This extra distortion can only be caused by the presence of hidden dark matter. Another piece of evidence comes from the cosmic microwave background, or the CMB. If you have ever seen that famous baby picture of the universe, you are looking at the leftover glow from the Big Bang. The subtle temperature variations in that image tell us a huge amount about the composition of the early universe. The patterns of these variations are perfectly consistent with a universe where approximately 27% of the total mass energy is dark matter. Without it, the pattern of the early universe would be completely different. Furthermore, dark matter acts as the invisible scaffolding upon which galaxies were originally built. In the early universe, small gravitational density fluctuations that eventually became galaxies were amplified much faster thanks to the gravity of dark matter. Without it, normal matter simply would not have had enough time to clump together to form the structures we see today. Essentially, dark matter acted as the gravitational seeds around which all visible matter clustered. Scientists are not just content with knowing it exists, they want to find out exactly what it is. The search for dark matter is one of the most ambitious and difficult missions in modern physics. Imagine trying to catch a ghost that barely interacts with the physical world. There are several strategies currently in play. One is direct detection. The idea here is to catch a dark matter particle colliding with a normal matter atom. These experiments are usually built in deep underground laboratories, well shielded from cosmic radiation. They use extremely sensitive detectors filled with liquids like xenon or argon, often cooled to cryogenic temperatures. If a dark matter particle, which is believed to be passing through us all the time, collides with a xenon nucleus, it could produce a tiny flash of light or a vibration that detectors could register. It is like waiting for an invisible billiard cue ball to hit one very specific atom. So far, there have been no confirmed direct detections, but the search continues. Then there is indirect detection. Some scientific models suggest that dark matter particles could occasionally collide with each other and annihilate. This process would produce normal matter particles that we actually can detect, such as gamma rays, positrons, or neutrinos. Space and ground-based telescopes are constantly searching for these leftovers in regions expected to have a lot of dark matter, like galactic centers. Finally, there is the production at colliders. In giant particle accelerators like the Large Hadron Collider at CERN, scientists smash protons together at speeds close to the speed of light. The hope is that in these high-energy collisions, dark matter particles might actually be produced. We would not see them directly, but we could infer they were there if the total energy of the collision does not add up. That missing energy would be the signature of an invisible particle carrying it away. So, what could this dark matter actually be? The leading candidates are not part of our periodic table at all. They are entirely new particles that exist beyond the standard model of particle physics. The primary suspects for decades have been WIMPs, which stands for weakly interacting massive particles. These are particles that have mass but only interact via gravity and the weak nuclear force. They are massive enough to have survived from the early universe and form the structures we see today. Another candidate is the axion. These are much lighter particles than WIMPs and were originally proposed to solve a completely different mystery in physics. If they exist, they would interact even more weakly with normal matter. There are dozens of other ideas too, ranging from sterile dark matter to even more exotic theories about a dark sector of particles that interact only with each other and with us only through the force of gravity. Dark matter is, without a doubt, one of the greatest challenges in contemporary science. It constitutes approximately 27% of the universe, which completely dwarfs the normal matter that makes up you, me, the stars, and the planets. Normal matter accounts for only a paltry 5% of everything. The rest of the universe is made of something even more mysterious called dark energy, but that is a story for another time. Knowing that most of the mass in our universe is invisible and undetectable by our usual methods is a humbling and astounding revelation. It forces us to expand our imagination and recognize that what we see with our eyes and our telescopes is just the tip of the cosmic iceberg. The quest for dark matter is not just the search for a particle, it is the search for a deeper understanding of the fundamental laws governing our universe. It is a universe that is far stranger and more wonderful than we could have ever dreamed. What other secrets await us in this realm of the invisible? If you enjoyed this journey into the mysteries of the cosmos, make sure to subscribe to the channel so you never miss an exploration into the great unknown. Watch full video in my channel. For more information visit minrora.com.